what I just said was this. Now we have presented EMD, and we find EMD generates infinite many sets of IMFs. And the question begging for answer is that how can we be sure that the answer we got is a good answer, or the answer we got really represents the true physics? So to settle that issue, then we need a confidence limit, at least to show how close this answer is to whatever we're looking for. Now the need of confidence limit is not limited to EMD. It's traditional method. We also have this issue. For example, we use Fourier analysis, but before you use Fourier analysis, you already made a big assumption. You say, well, sinusoidal function or trigonometry function is D-base. Yeah, there's no guarantee that it should be D-base. Yeah, we can find infinite many wavelets, and which of the wavelets is better. Now, if you can only establish that the confidence limit is relative to A base, that does not answer the question. That only answers a mathematical question. That is, hey, this method is stable. Whether the method is stable also represents true physics is another issue. So establish confidence limit, however, will give us some comfort to indicate that the method at least is stable, is good. Now, the confidence limit for Fourier spectral analysis is based on ergodic assumption. Now, what is ergodic assumption? Ergodic assumption is a long statement. It says that if you have a process that is statistically independent, and of course that also implies linear stationary, then what you can do is that you can represent the ensemble average by temporal or spatial average. What's ensemble average? Ensemble average means you have independent trial. Like, for example, we're in the physics laboratory. We want to see a ball rolling down a slope, how far it can roll. Now we'll do it once, it rolls X meters, and then we roll another time, it go to X 1 meters, and it roll infinitely many times. Then we average. We'll find the average distance. So whether the true answer sometimes resides not in just one measurement. You have to make many, many measurements. And these many, many measurements you made are statistically independent, then you can average it. Once you average it, you hope you'll get the true answer. And if not, at least you know that the scattering of this answer give you a limit of how far off you might be from the true answer. Now, ensemble average means that you have to do independent trials. Not all the process that we can always go back and do it once, do it twice, do it 3 times, and do it so many times. Most of the data that we got maybe 1 trial. And from that 1 trial, how can we get an ensemble average? We cannot. So we invoke the ergodic assumption. The ergodic assumption is that I know I cannot get independent trial. But if I get 1, then I can chop this into sections and take each section as an independent trial. And each section, we put it all together, average it together, I will get then basically the true answer. So there's a big assumption there. That's ergodic assumption. Ergodic assumption, however, it's most of the time we just assume it's valid. No one, I seldom see anybody go through the trouble to show that their subsection is indeed statistically independent and all the other properties. Okay, so by dividing the data into M section, and substitute the temporal space average as the ensemble average. This method is only valid for linear stationary and statistically independent components. By dividing the data into subsections, we also sacrifice the resolution of the answer. So, so we will see how this different trial. So what is independent? Independent means that if I have variable x and variable y, and the joint probability distribution equals to the product of individual probability density function. Not many statistical processes satisfy this. The joint density is not simply product of each individual. One thing, however, the independent variable are non-correlated. They're uncorrelated. Now we can try that very easily. Now, for example, we come back to this example. We'll use this example repeatedly. This example is the length of day, and this is very long. This is, as I said, 40 years, and has 14,000 data. And if we use Fourier analysis, we'll get two sets of answer. One is this, the other one is that. Yeah. The set of this set and this set, if I plotted without any change, this set and this set will actually fall right on top of each other. Yeah. But I divide this by 1,000, I move it down so that we can see the difference. This is the spectrum of all the data, of 14,000 data points. This is the data that I divide the whole data into 7 equal sections. Each one is 2,048 points. So this, I only get one shot because this is the data length. I get a spectrum, that's it. And because the data is very long, so my resolution is very good. The resolution of this is 1 over 14,000. So each spectrum, each individual data point is 1 over 14,000. But by dividing this into 7 sections, so my data is, each data is only 2,048. So each of this point, the distance between this point is 1 over 2048. So this has much coarse, much worse resolution than I got it here. But because I divide this into 7 sections, I have 7 individual answers. And these 7 individual answers, I can put it all together. And put it all together, that's what I got. Now you have to realize that once you get this average, then you have average and the standard deviation. Those standard deviation says, okay, you try the 7 times, the range is roughly around here. But if you plot this spectrum over there, do you see that the spectrum will actually goes up there? Is that true or not true? The answer is this probably is also true if you have a resolution good enough. But once you subdivide into 7 sections, you will never be able to recover that kind of resolution. So by doing this confidence limit, you actually sacrifice the resolution that you originally have with the original data. This is what the Fourier will get. So the next question we ask, so are those subsections statistically independent? Well, we don't know. But we do know one thing, is that in the narrow band signal, most likely they will not be independent. Why? Because they are not totally uncorrelated. Statistically independent should be uncorrelated. If you take that data that I show you, and if you run the correlation function, you'll find that they are cross-correlated because the annual annual cycle is so strong. So, and now we know how we got confidence limit before. Now we have to discuss how we get a confidence limit for Hilbert spectrum. For Hilbert spectrum, since any data can be decomposed independent into infinite many different components. Yeah, the EMD method is based on the different shifting parameters you generate that. Just like in wavelet, it's based on different mother wavelet, different the basis foundation. You can generate many different wavelets. So some of the IMF are better than others based on various properties. For example, orthogonal index. That's one method that I use, one criteria I use. So you get one, you get another. How do you know this is better than the other? Well, one trial is to see how orthogonal they are. If they are not orthogonal, the energy is not totally conserved. In other words, x squared does not equal to summation Cj squared, equal to Cj squared plus 2 times Ci times Cj. So orthogonal index is one of the parameters that I use very often to judge whether an IMF is good or not good. Now, confidence limit for Hilbert spectrum analysis can base on an ensemble of the valid IMF. In other words, what is a valid IMF? If the IMF is grossly out of orthogonality, I will not even include it because that's bad. I should not use it. Okay, so for that, how can we get different IMFs? There are many different ways. So one of the ways that I use is to use the stoppage criteria. That's the easiest way. I use different stoppage criteria. I can use stoppage criteria. We listed, I will get that. And the nice thing about this method is that it's valid for nonlinear and non-stationary process. We don't have to make the assumptions of stationary linear because I don't compare one section with the other section. By the way, when we do that Fourier spectrum of that the length of day, we have to take the trend away. Otherwise, some section will sit on the slope like this, other sections sit slope like that. Then the average will be very bad. So we don't make that stationary and and nonlinear and the linear assumptions. Now we can actually generate all kinds of different confidence limit based on different criteria. Now the basic idea is that if we try to generate a different set of IMFs and treat the mean as the true answer, then we will get the confidence limit that way. So how many different IMF we can generate? There are a few examples. We can use stoppage criteria. We can use downsample. Downsample is very similar to the subsections, but not exactly. The subsection is that instead of chop the data into different sections, I take the data, maybe take 1 and skip 3, and then skip 3 and skip 3. So I take 2, skip 3, and skip 3. So I get 4 sets of different data. Then I would do the 4 sets and then average that. So that's downsampling. We'll get to that. And we can even do different spline. We can do natural spline, and we'll say, well, natural spline may not be very good. I want to do Hermite spline. So you can do Hermite spline, and then you average, you try to compare the two and see how different they are. So different ways give you different IMFs. One of the methods I did not discuss is this. This is the subject that we're going to discuss next time. That's ensemble EMD. And ensemble EMD is very different. That is almost like a true ensemble. Yeah, we'll discuss that later. But the idea is that we can indeed get a different kind of ensemble average. The idea is that you do this and you get this IMF. To get this IMF, how do you code this C1, your first component? This depends upon stoppage criteria, right? But none of the above method above method depends on the ergodic assumptions. Yeah. All the method we do, we don't have to say that this is stationary, this is independent. We just keep on trying. One, try another. Yeah. So we almost achieve a real ensemble mean. Now in this particular case, however, we're using stoppage criteria. We have 4 different kind of stoppage criteria as we discussed. And here, I will use the SD. I'm sorry, not SD. I use the S number. This I will count how many times I shift. I will get the answer. Now, this will depend upon the shifting machine that you use, how you decompose. I have posted that shifting. Did you post that on the web? The shifting HHT EXE. WHHT. Yeah. So you can download that and play with it. And maybe next time I'll show you how to use it, how to get into that. Okay? We'll have time. So in there, at the beginning, there's 2 boxes on top. You will choose whether you use intermittency or not use intermittency. So you can choose the use intermittency. And one of the parameters what you want to use is to choose the capital N. That is how many shifting you want to implement. And we did that. That should not be a consideration if you use the stoppage criteria, as I said, the counting extrema equal to 0 crossings. But we did put in an N in because that tool was used at the beginning of developing the method. And some of the spline that we use does not converge very well. If you do not put a capital N, says how many total iteration you want, and sometimes it keep running day and night and never stop. And we waste a lot of time. So we put a capital N there. It's after 100 times or after 200 times. And if you want to be ambitious, you can put it in 1,000 times. Okay. But typically, I put it 100 times. That's a lot. This is just to ensure that we'll not get into a dead loop. This is not a guarantee convergence. This is a guarantee that we do not get into a loop. But later we found this is not important once you use, for example, you use cubic nature spline. They will never get into loop. The criteria for accepting a shift component as IMF is the stoppage criteria S. Yeah. So when you use that shift machine that I give you, you should always remember whether you use the extrema or you use curvature. That is also a choice. You can choose to use curvature, you can choose the extrema. The answer will be different. Yeah. At least it will be different slightly. So that makes sure that you keep track of that. And you can play with that. Now, all of you have at least two sets of tools. One is the WHHT. That was the program that I used, start from 1995. Yeah, and it's been more than 10 years. I still use it sometimes. The other set that you use is the one that posted on the also on our web. Is the ensemble average, ensemble EMD. You can use the ensemble EMD to do the same thing. Put the noise equal to 0, and put this ensemble number to be 1, and that you just do it once. Okay? So the ensemble EMD can also be used like this. But the ensemble EMD does not have curvature, does not have intermittency tests. There's still another one that which I use most of the time. That was the one that given by NASA. And unfortunately, I cannot give that to you because NASA does not want to share their software with other people. Yeah. So, but the software that you got should be sufficient. Okay. Now, there's another one, shifting with intermittency test. In the software that I give you, WHHT, there's a box that you can check with or without intermittency. Now, if you check with intermittency test, they will ask you just whether I would do you would do intermittency test. What is the shortest wave that you want to set? So the criteria is up to you. And if you choose one, once you choose one, the next one will be twice the wavelength. So if you choose one, the next will just follow. But sometimes one time is not enough because there are many, many embedded short waves. So you may want to do more than one time. So then you have to come back and repeat that. Next time, maybe I will demonstrate how to use that WHHT. It's a very useful, it's an interactive kind of shifting that you can play with it. It's very nice. Do you have WHHT internet? You have that, right? It's already in the computer. Do you have data there? Well, how about this? Next session, I'll ask you to make a demonstration of that. Okay? I'll ask Mr. Su to demonstrate how to use that. And make sure that you want to show that you use different with or without intermittency, and choose the criteria and repeat it. Okay? All right. So we will. So the intermittency test, we'll come back and visit that many more times. This is the intermittency test. We have already covered that. So we'll go very fast. So if we have intermittency test, so make sure that you put another name on it. So the result you got, at least you can come back and repeat it. So what I use is component with extrema and intermittency test. That N is the total number of shifting that I use. S is the stoppage criteria. And then the first components, what is how many number of wave that I use. The second component is how many wave you use. Okay? And this, once you record this down, anybody come back and do the same thing will get the same answer you got. Yeah. And this is important as a reference. And I think it's very, very important to keep a record for yourself. Now, the N effect of the shifting. To separate data effects of EMD. Why we do EMD? What EMD will do? EMD will do actually two things. One is to eliminate riding waves, the wave right on top of the other. The other one is to make the wave more symmetric. To make wave more symmetric, in other words, the upper and lower envelope will become symmetric. That means the zero line get very, very near zero. That require actually your neighboring wave becomes very, very similar. The amplitude becomes similar. So the EMD has another side effect is to make all the envelope approaching to more and more flat, or all the amplitude becomes similar. So this EMD, because of this, the EMD is a two-sided sword. If you use it too many times, you'll get an FM signal. The amplitude is all constant. Then there's absolutely no information in there. If you use it too few times, you may not even get an IMF. So what is the optimum time? Optimum number of iteration that we use? That's another issue we have to answer. In this lecture, we are going to cover most of those things too. All right. So the effective, so to sift this, then we will have to look. For example, this is the data, and we start to sift it. Here, the name is CE102. This result I got with maximum 100 times iteration, but the stoppage criteria equals 2. And here you see I got a pretty good answer. The half-monthly cycle, it's very good. The monthly cycle is also acceptable. And even if you look at the annual cycle, the annual cycle, there are some parts which is not very good, but typically it looks sort of half yearly. And even if you look at yearly is still good, but except when you come down here, you find that you have problem. Yeah. We'll come back to tell you why we have problem near the end. Okay? That's not end effect. It's something else. So typically this looks like a yearly cycle. This is stoppage criteria 2. I can't extrema equal to 0 crossing. If that equals to m, if the second time, shift another time, it also come out to be equal and equals to m. Then I stop. This is equal to 2. Now, if I want to be a little bit fancier, I say that the top maximum iteration is 100 times, but I will count 10 consecutive times. 10 consecutive times. I count 1, I count 2, count 3, count 10. Now you see, this answer is very strange. This answer is what? You see this component? I cannot see annual cycle anymore. The annual cycle disappeared. The annual cycle gets scattered all over the place. Here maybe looks like annual cycle, and this looks like annual cycle, this looks like annual cycle, this looks like annual cycle. The annual cycle is scattered all over the place. Compared to this and that. You see, here is the annual cycle, and you compare that with, you see, the annual cycle is the fifth component, and if you look at this fifth component, you do not see annual cycle consistently. You see here, compare that to this. They are different. We have a very severe mode mixing problem. Yeah. So, should we say that 10 stop criteria equal to 10 is totally invalid? Not necessarily. Actually, even this is still a good decomposition. But the good decomposition, by looking at the EMD, it's not conveying the whole physical properties. For example, another thing that we start to see is that toward the end, you see we have very nice half monthly. But come to here, we don't even see continuous half monthly time. This is still far from the end. So what is the cause of this? The cause of this is our data. We have very smooth data over this section. At the 60s and 70s, we don't have very good observation of the rotating of the Earth. So the rotating speed of Earth sometimes will have to be determined by a few days of continuous observation. I observe it today, I observe next day, and then I will average. Okay, I will interpolate to get this. So this is very, very smooth answer. This is a smooth answer. When you interpolate the answer, you have to have some sort of model, and that model is based on, say, I know we have tide, so the very clear tidal cycle. But once we move, as time goes on, we get a better and better answer, better result. By the time we come to the 1995 and beyond, we have so many GPS satellites. We can really measure the rotating speed of the Earth. We not only can, we will have no interference from the weather. We can always get a measurement of the rotating speed of Earth. We not only get one answer for, we don't need many days to get one answer. We get in one day we get many answers. Okay, so because of that, the data is so good that we start to actually see storms. Yeah. If we have a big storm, a large storm, see, I explained to you, if we have El Nino, the El Nino give a little bit more energy at the equator, then the atmosphere will move violently, so the rotating speed of Earth will slow down. Now, what if I have a huge storm? The storm is not just one hurricane or one typhoon, but a huge front. That front just suddenly move, Siberia cold front just suddenly move, come down to Taiwan. I have never seen Taiwan becomes very cold because of the ocean influence. But in United States, sometimes a Canadian high can come down so far down to Florida. And Florida actually can freeze. And that is when Florida freezes, that causes a big havoc because the citron, the orange, and the grapefruit, the fruits will all be ruined. So that big weather system can cover the whole area of the United States, not just cover a few hundred kilometers. That kind of big storm, big fronts, can actually influence the rotating speed of the Earth. And previously we cannot detect that. And now we can. Now, since this storm front has a typical time scale of 7 days, not half month. So the 7 days signals start to appear here. And that resides here. So it push half months over here, and then push monthly over here. So you see, this data, they get a very high frequency data here, and get a high frequency data here, and so the annual cycle get pushed down to C7 rather than C5. Yeah, you can always see that at this end you get a finer scale, and when you get a finer scale, means you get a finer data. Yeah. Much better, much detailed data. So we get much detailed data. Increasingly, we get better and better data. And this better data push our components further down. Whether this is better than that, it's hard to say just from the eye. So what we want to do is we want to make a measurement. Just which one is good. So the way to do that is that I use the orthogonal index as a criteria. I try to measure which one is good, which one is bad, based on its orthogonality index. You can use other criteria. I will tell you other criteria later. Now this graph has it's a surface. On this side is the maximum number of shifting n. Yeah, I put n as a independent variable. I put it n equals to it is log. This log 10 base. n equal to 1 is 10 times, n equal to 2 is 100 times, this is 1,000 times. Okay, now you can see that these streaks are all constant. So in other words, after 100 times, you don't have to tell me I stop at 500 times or stop at 1,000 times. It doesn't make any difference. They are the same. In other words, after 100, but below 100, however, well, later I will show you a section. Below 100, there is some variations. There is some variations below 100. But after 100, it's straight. So the maximum shifting, maximum iteration, if you choose 100, that's sufficient. That's why I can tell you, because I did the test. But below 100, there are some variation. The variation is not very big. What this on this axis is the stoppage criteria 1, 2, 3, 4, 5, all the way to 10. In fact, I used more than 10, but I only plotted 10. Here you see the stoppage criteria over here. By changing stoppage criteria, we have a drastic influence on the orthogonal index. It changed from very, 0 is here, by the way. 0 is not here, 0 is here. We have a very negative orthogonal index sum of almost near 0.25. And suddenly raises. We want to be mostly in this region. Mostly in this region. It actually get into mostly that region by the time we go beyond 4. So beyond 4, we are on this plateau. On that plateau, the orthogonal index is between plus minus 0.5. Now, I will accept 0.1 is 10% orthogonal index. It's, to me, it's good enough. But once we go beyond that, we actually sit over here. This plateau, the orthogonal index, are all very good. Now, this, so I did an extensive study and tested out and found the orthogonal index roughly is good, except that here. I will show you another section of, another view of this. That is, I cut sections. So we'll look at the data from this point of view. Okay. So by cutting sections, you will see that this line is for n equal to 10. That is the maximum number. I only said after 10 trial I'll stop. After 10 times I will stop. You see the orthogonal index sometimes drop off pretty severely. Yeah, and especially on higher number of stoppage criteria, you have to count 8 times to stop. So that just 10 shifting is not enough. But once you go beyond 10, like 20, 30, 40, 50, they all bunch together pretty tight. Yeah, all bunched together pretty tight. The only thing is that you really do not want to say the first time you get the extrema equal to 0, you stop. And that time, the orthogonal index is very low. Yeah, and that's stoppage criteria equal to 1. Now each one of this does not mean that they are actually separate. I offset each by 0.1. If you do not offset, all these curves are all bunched together. Okay, so the whole thing is much tighter than your eye. I purposely offset each delta by 0.01. Yeah, so 0.01 is this distance. So if you do not offset, they are all equal. Yeah, I use n equal to 1,000 as my reference. So this will be all together. So now you can see that using 1 is perhaps not very good, at least based on the set of data that I test. Yeah. I test a few sets of data. I did not test every set of data because this is very time consuming. Yeah. Now, once you get to 2, immediately the orthogonal index jump up to here. Jump up to here. See, this is my reference. Everything is offset over here. So all of this will all converge back to over there. So my orthogonal index is probably only 0.02. It's only 2%. It's very respectable. And, and then it fluctuates as it goes further, except that this one does not belong to the patch. This one is n equal to 10. But unfortunately, later, when you use the ensemble EMD, the iteration time is set at 10. Okay, I will explain to you why we set it at 10. There are reasons, but that was 10. So we can see, in this way, we get an idea of how strong the stoppage criteria influence the answer. Now, confidence without the intermittency criteria. In other words, this is what I had. I just push the button, it goes through. Okay, but this is very, very. It has a severe problem. That is, if you do not do anything, you just say go. I set stoppage criteria equal to 2, it will go. And if you set the stoppage criteria equal to 3, it will go. Now you can see that at the beginning I say stoppage criteria 2 and stoppage criteria 10. We'll go back to that. See, stoppage criteria 2, we get 9 components. Stoppage criteria 10, we get 10 components. Even the component number are not the same. So in this case, we cannot average the components, right? One set I have 10 components, the other set I have 9 components. And how can we average them? So the number of IMF with different shifting may not be the same. Therefore, we cannot average IMF. The IMF does not have its full range of physical meaning. Okay, so what we can, however, is to average the spectrum. What is the spectrum? I jump a little bit ahead of my time. The spectrum is that you project this IMF in time frequency space. In the time frequency space, we put each beams. We have equal number of beams. So the spectrum number 1, I have, say, 1,000 time step and 1,000 frequency step. And the second one, I also have 1,000 time step and 1,000 frequency step. And the argument that I had at the beginning is that, sure, you may have some fine-grained solution, but that yearly cycles should still be there somewhere. It may not be at the IMF 5, it has to be at IMF 7. So if it's 7, I can still pick it up, I can put it in the time frequency space. I did not lose the solution. So if we make everything, project everything on the spectrum, we can average it. So let's see. This is the spectrum that with stoppage criteria equal to 2. Yeah, stoppage criteria equal to 2. We can see this is the half monthly time. Half monthly time. That's half monthly. It's not 24. This is lunar month. So we have a little bit more than 24. It's almost 26 or 25 or 26. And also, this is not just a line, but it's oscillating up and down. Why it oscillates up and down? Because the tidal wave, the tidal range, is not a sinusoidal function. And at the beginning, in the introduction, I have shown to you that if you want to decompose the tide into sinusoidal function, you will have hundreds of components. the so-called harmonics. Yeah. So that harmonics is all resided over here. It's also up down. This is half monthly. This is monthly. Monthly instead of 12, it actually get way beyond 12. What happened is that over 19 years, the lunar month contains 7 extra months. So in 19 years, we'll leap 7 months. So each year, we have almost half a month extra. Yeah. Then this is half yearly, this is yearly. So we see all this, just like we see the intermittency test. We see all the scales over there. And we also draw your attention to here. After 1990, especially after 1995, our data becomes so diffused and so noisy because we have much, much better data. And that much better data actually push this down a lot more. So this is the stoppage criteria equal to 2. Stoppage criteria equal to 10, it's different. But if we average, I have done 2, 3, 4, 5, all the 1, 2, 3, 4, 5, all the way to sometimes to 20. And what do we got? Once you average, you see the average. This it's much better than the individual. Once you average, this becomes more coherent. This side becomes more coherent. Yeah. So I can indeed average it and get a much more coherent signal that will come out through the ensemble. Yeah. Each individual trial give me individual answers, but each answer comes back to give me a total answer like this. And this, in this case, we can all this is the standard deviation. So we have a mean. Now we also have a standard deviation from all the trials. All 10 trials, you see the standard deviation is that whenever you have answer, you have numbers, your standard deviation usually is higher. Yeah. And this is the marginal spectrum. So you integrate everything. You integrate the timeout. So what you have is here is the mean. This is the standard deviation. So this is annual cycle, half annual cycle, month, half month. The half month is bimodal distribution, and that indicates that we do have intra-wave modulation, just like the Duffing waves. Yeah. Now, you look at this, you say, gee, this mean and the standard deviation looks awfully close. Not really. If you plot in this way, you see this annual cycle is big, and the standard deviation is around 0.1, the annual cycle is 0.01, this is almost 0.001. It's standard deviation is about 1/10. Compared to the signal, it's still small. So the standard deviation, we do have a pretty confident reading on this. And if we plot all 10 different trials, here is all 10 different trials. You see, this end is very tight. It's very good. And as we go lower and lower frequency start to separate. The lower frequency, we do not have a lot of confidence because of the limited length. So if we plot the annual cycle, and if we also plot the 95% confidence limit, we have a very tight peak. Around the peak area, it's very tight. And around non-peak area, we have a big separation. In other words, when the energy is low, it indicates that the average is not that that good. When you have high energy, it's always peaking up. And this side is very tight. The 95 percentile confidence limit is almost coincide with the curve. Now, then we'll try with intermittency. Here, with intermittency, I will first set the criteria. I say I want to have the extrema number. The criteria is 4. 4 means from zero crossing to another zero crossing, 4 points. Okay, so whole wave has up zero crossing, down zero crossing, up zero crossing. It's has 3 zero crossings. 2 zero crossings, 1 wave, right, on average. So this is only half of the shortest wave. 4. 4 means the whole wave, the whole cycle is 8 data points. That means 8 days. 8 days, it's very far from the half monthly. Half monthly is 14 to 15 days. Yeah. So I want to get rid of this 8-day cycle. 8-day cycle is already longer than the frontal time scale. Frontal time scale is about 5, on average 5 days. So you first use that, you immediately take away all these tiny little oscillations. The tiny little oscillation only occurs here. Why it only occurs here? Because our data is much better. Prior to this, we do not have enough GPS satellite. We do not have enough the space geodesy, so we do not know the rotating speed of the Earth as detailed as we had before. This does not mean we don't have storms. We do have storms over there. But the storms, the influence of storms, the effect of storms are all averaged out. So we only start to see that in the last, say, 15 or so years. Now, once you take that away, immediately you have a very nice half-monthly cycle, and you have a very nice monthly cycle, and you can force that, force half-yearly and yearly. See, this yearly cycle looks very nice. Yeah. So by using the intermittency, we got we can improve the answer. Here, for example, I used 45. I used 2 times. It's 4. I used once, and this component I did not use any intermittency at all. So I will get monthly, half monthly, monthly automatic, and then I use these 3 components without intermittency. Then in order to push all the half-yearly cycle to the same component, I use 45. 45 it means 90 days. 90 days compared to half-yearly is 180 days. I'm still 1 octave away. So I'm pretty safe. I get half-yearly and yearly and beyond. And this is with stoppage criteria 2. And with stoppage criteria 10, I get very nice. See, I don't even, oops. Here, I still get some blemish over this region for yearly. And if I use criteria equal to 10, I extract the annual cycle and half annual cycle very well. And by using the stoppage, using the intermittency, I gain another advantage. That is, I will always get the same number of IMFs, because I can adjust this to control how many IMF I got. So by using this, I got, say, using 2, I get 12 components. Using 10, I get 12 components. Even though the last component, this is almost constant, but this is still a little bit cumbered, but it's all 12 components. So in this case, I can average IMFs. I don't have to average only the spectrum. Of course, I can still do the spectrum, but I can average IMF. And by average IMF, I can plot out this IMF. This is with stoppage criteria 2, stoppage criteria 6, stoppage criteria 20. They ranged this far away. And if you start to check the orthogonal index, with stoppage criteria, then you will see the orthogonal index fluctuates. But this is 0.1. So we're always below 0.1. So the stoppage criteria, it's okay. With different kind of stoppage criteria. And if I average all the different cases, now previously I wasn't able to average the IMF. Now I can even average IMF. I average IMF, I get very nice annual cycle, and very nice half annual cycle, and also very nice monthly and half monthly. I get all the components out. And each component, because there's no scale mixing, I'm very confident of the answer. The answer has a physical meaning, half yearly, yearly. So when in the introduction, I showed this is the answer I show. I did not mention this because this is the storm. This is a much shorter scale. So now I can average this. Now, when I can average this, then each of this, instead, in addition to the mean, we also have a standard deviation. The standard deviation turns out small. The standard deviation are very small. Here, of course, we get standard deviation because that's the only place you get the signal. Over here, for example, you see the annual cycle. The annual cycle is small, except in this area and in this area, it starts to flare up. And that's very interesting. We'll come back to here to discuss this. This is during 1990 to 1995. 1990 to 1995, we have big anomaly. So we have both average and standard deviation. And the standard deviation, for example, here is 0.02. If we look at this is 0.5. And the standard deviation here is 0.2. So the signal is much higher than the standard deviation except this region. Even in that region, it's only 0.2 compared to 0.5. The rest of the area is much, much smaller. Now, if we project it into the frequency, into the Hilbert spectrum, you see how nice this is, and especially you see how coherent and how continuous the annual cycle is compared to the previous case. Let me see, I have this. This is the standard deviation. See, previously, the annual cycle and the annual cycle standard deviation is almost visible. Here, it starts to disintegrate. So this is a much more reliable answer. Not only that, if we look at the the marginal spectrum, this is the marginal spectrum. This is the standard deviation, and you compare the marginal cycle with the standard deviation, and you plot the all 9 cases, and you find that it's very tight again here, except that here in the low energy area, you still have some more scattering. But in most of the case, however, the energy peak area are very good. So you compare this with this. This is the one. This is with the one that without intermittency, and this is the one. This is the one with intermittency. I will draw your attention to this area. You can see this. If you concentrate in here, you find that the dynamic height, dynamic range of this increase a lot. So with intermittency, you can indeed improve the sharpness of your answer. Yeah. Now, if I plot the annual cycle, all 9 annual cycle, all here, then what you see is that most of the annual cycles are very coherent, except in this region and also in this region. Of course, the end, we have a little bit of problem in the end. But internally, here and here, we have problem. That's the area that we have high standard deviation. And I blow it up. This is 1991 to 1990. Between 1990 and 1995, we do have a large standard deviation. And that, because I used to work in the ocean area, I know the reason. Between 1990 and 1995, we have a large anomaly in El Nino. And some unfortunate oceanographers tried. At that time, the computer is good enough, the model is good enough, so that gives a lot of ocean modeler a lot of confidence. I can predict El Nino now. So they come out and predict El Nino. And everyone that tried to predict El Nino all failed because of this anomaly. Yeah. The equatorial region is continuously warm, and it never really get into the clear pattern of El Nino. Yeah. And in this very simple exercise, and we actually identified the troublesome regions. And that troublesome region, the annual cycle is unclear. Or at least some components are unclear. So in other words, in this region, we do have some confidence limit issue. That is, you can call it a year, may not call it a year, and so nobody know what it is. It's the anomaly region. And and if you plot the annual cycle, this is the mean. And if you plot the anomaly, you see this area, the anomaly is very, very high, and this area is also very, very high. If you visit the U.S. NOAA site, the U.S. NOAA site will alert you that 1990 and 1995 is an anomaly El Nino period. 1965 to 70 is another period of anomaly. Yeah, and that all showed up in our standard deviation. That's the two large standard deviation anomaly areas. And and indeed, if you look around, so we have very large scatter over here. This is from here all the way down here. As in the other area, we do not have that kind of anomaly. Yeah, and this is the mean. This is the anomaly. This is the anomaly is large here. Anomaly is large here. This is the standard deviation. So we going through this, we got at least one confidence limit. We know that if we go through this, the answer we got, how confident we are. We find that even though we change the stoppage criteria through a very large range, the answer is still about the same. The average, the standard deviation is not that big. That's fine. That's great. But the next question then back is, okay, then when I do a problem, should I do it all 10 times on the average? Is there any guidelines for me to find what are the better S value to use if I want to do it just once or do twice instead of do 10 times? So the optimum shifting parameter is an issue that is still unsettled, that is still outstanding, and that we ought to keep on looking for it, and I'm still looking for it. And I will just report to you right now one of the effort that I made, and I found certain range. And later I will report to you other kind of trial. Here is we're trying to see what is the best parameter that we choose can guarantee or at least give us an indication based on the confidence limit. What kind of range we should we should use. So the maximum CPT number should be set very high to guarantee that stoppage criteria is always satisfied. In other words, based on this, we should not say the maximum iteration time at 10 or at 20. That doesn't work, we can see. At least we want to go beyond 20, 50, 60, or whatever. The second is stop criteria should be selected we want to make the difference to be minimum. Yeah. And the difference can be computed from the Hilbert spectrum or the IMF components. If we can select the IMF components, and if we can select the IMF components so that the individual separation is small, and that means the answer is stable. That means the confidence is high. So in addition to the stoppage criteria, we can also use the scattering of the answer as an indication. If I use 2, I use 3, use S equal 4, use S equal 10. All of them give me the same answer. That means I don't care. This is going to be a good answer no matter what. But if you use 2 and use 10, the answer is dramatically different. Then you know that maybe here I have to be very careful. So it turns out that the IMF actually is a much more sensitive criteria to compare. Sometimes we cannot compare IMF. We can still compare the spectrum. Yeah. So if we can compare IMF, by all means compare IMF. The IMF actually has more, give us a little bit more coherent patterns. So the next thing we want to compare is that if I have a variable, whatever variable I have, and I average this variable, I will get, say, equal weighted average, I get the average value. Then I want to compare the scattering. That is the value, the mean value minus each individual trial value, square. So plus and minus all becomes positive, and that equal. This, by the way, this is equal. I don't know why the PowerPoint will not pick that up. So to do that, I have done many different stoppage criteria. For example, like the stoppage criteria IMF for with intermittency, I just pick up the annual cycle. The annual cycle I get the average, right? And average, I can take that average and minus each individual and square. So then we can find out the variation of that value. Variation of that value as a function of stoppage criteria. We'll find over which area the answer is closer to the mean. If a value, that the answer is very close to the mean, so then the individual value minus the mean will be small, and so then I don't care. I don't have to do 10 times. I just pick that as number, I just do it, and I will get almost near the mean. So this is a way to look for optimum shifting time. Then we will see that if I use stoppage criteria equal to 1, the difference between that particular value and the mean is very large. Yeah, so I know stoppage criteria equals to 2 is probably not very good. And stoppage criteria equal to 3 is also not very good. But by the time stoppage criteria equal to 4, the difference between that individual 4 and the mean, this average, it becomes very small. Okay, I did not normalize this. Perhaps I should normalize it, divided by whatever, to give me a percentage. But this is just a raw plot. Now you see that by the time you come to 4, it's already small. Come to 5, it's smaller. Come to 6, it's smaller. Comes to 7, it starts to pick up again, and if you go say, all right, I want to go to 20, consecutive count 20, and by the time you consecutive count 20, you're not improving your answer. Why you're not improving your answer? Because you have already pushed the amplitude to be so low. And it almost becomes FM. So this answer is not necessarily good. So if you go too high established criteria, it's not very good. Too low is not very good. Ideally, I really want to find a well type of thing. I found a minimum range. Here, I don't have a perfect well, but I do have a bottom region between 4 and 8. That's a pretty good region for me to use. Established criteria equal to 4, established equal to 5, doesn't matter. This is for annual cycle. And if I use a half monthly cycle, tidal cycle, then I will see, start from 2, and I drop to 3, it's very good, and the 4 comes up again, and 5, and again I have a low region. By the way, recently I'm continuously doing this for other studies, and I will report that to you later. I find that number 3 is very interesting. Many times, by number 3 drop, number 4 up, and number 5 drop again for different kind of data sets. I don't understand why, but this is a curiosity that I find that it clicked. But anyway, so we still find a region over here that the individual case and the average getting very close. Yeah. So case after case, we can try. For example, we can use Hilbert spectrum. Deviation from the mean of the Hilbert spectrum. Previously, we plot IMF. Now I use spectrum. I have a mean. I have each individual spectrum. I have the mean average. The mean and individual can have difference. So this is actually the mean minus the individual spectrum. And again, lower case is no good, higher case is no good, and over the intermediate range, each individual spectrum looks very close to the mean. Not exactly equal to the mean, but close to the mean. Over what range? Over to this, again, this range, 3 to 8. Yeah. It's not a perfect smooth well, but it looks like that over this region the difference is small. What does it mean, difference is small? Difference small means that's a more stable region. Over this region, it changed very little. So if it's changed very little, it means it's very stable, and it's very stable, that means the answer is more believable. And if over here, that means it's erratic. My individual case and the average overall, it stands way above. Yeah. So to believe in mean, it's almost axiom. That means no one can really prove it, but it works. Only recently, 2 weeks ago, I read an interesting paper. It said that the average of large number really works very well. It does not even depend upon your knowledge. Yeah. The example they took is that they collect like 100 people in the room. They get a jar of jelly beans. You know, jelly beans, little 小糖球, put in a jar. They ask each one to guess, so how many? It turns out no matter how good you are, you will never guess it perfect. Okay? So everybody made a guess. And it turns out the average value comes out very, very good. Always very good. And they tried all kinds of different tests. it's all come out very good. So a large number of try and get the mean sometimes really works wonder. Here, we depend upon the mean. So if we try many times and over this region, the value differ from the mean is smallest. So that region is the is the most stable. Here we try not only on individual IMF, we also tried on the whole spectrum. And we try individual spectrum with CE. Here CE is without the intermittency test. Then that you start to see that in large number, it does not deteriorate very much, but still the minimum is around here. There are some anomalies. You have you can try different different cases. You may average out the difference. But by and large, in this region, it's usually small. And all of this is with only one set of data. This set of data is the length of day data. So I want to try earthquake data. So from earthquake data, this is earthquake data. I believe you can, has anybody can download this data? Yeah, most people can download this data from the Weather Bureau, Central Weather Bureau site. So I use this data and I do a mean Hilbert spectrum. This is the mean Hilbert spectrum of that particular sets. And I just average the using earthquake data and tried on the stoppage criteria. And what I got is that, again, if I have very low, only the first time it works, it's very bad. And 20 times is also very bad. Yeah. So we have a general well shape, but here we have not smooth well, but it's from 2, 3, 4, 5. It's all in the lower region. Yeah. So I don't have a absolute proof that stoppage criteria equal to 4 is better than stoppage criteria 3 or stoppage criteria 5. It's getting worse than 4. There's absolutely no proof for that. But by the number of trial that I have done, I find that in this region, the stoppage criteria are very nice. So in this way, so we almost can deduce an optimum range of stoppage criteria. The optimum range of stoppage criteria is from 3 to 10. But you want to go 10? Perhaps not. I will advise against that because A, that takes a lot of computation time, and B, it will actually suppress the amplitude. And also, if you take a higher stoppage criteria, and you have worse and worse mode mixing. Yeah, because you really separate the scale locally separate. And by locally separation, the scale mixing will become even worse. Yeah. So by the time you get such a high value of stoppage criteria, the mode mixing will become so bad that each individual IMF totally lost its physical meaning. You have to go back, project it back to Hilbert spectrum. But as I said, Hilbert spectrum is such an average, it's not very sensitive compared to IMF. So if you can get a clear IMF, it's much better. So this selection agree with our past experience. However, that's not a proof. That's just a few points in my empirical approach. Yeah. You may want to try this. I don't have a standard data, I believe that each of you perhaps have your own data. Maybe you want to try one of this with to try the optimum range of stoppage criteria on a set of data of your own selection. But don't select too long a data. That will take too much time. So I will assign this as one of homework. You try to see which criteria is better. Okay? So that will be our homework. Oh, by the way, I don't think I have final examination, so your homework will be your final. I'll give you a grade based on your homework. So if you don't turn it in, then I have no reference to give you your final grade. So be sure that you hand in your homeworks. Okay? So summary. The confidence limit represented here exists only with respect to EMD method used. I used the EMD, I established a confidence limit, and in this particular case, I used IO as a criteria. We can use other as criteria. For example, I can use standard deviation, like the standard deviation of IMF, standard deviation of a spectrum, that are all very good criteria. So you can think of different way to judge which value is better, and you can use different criteria to establish the confidence limit. Yeah, instead of stoppage criteria, we can use different spline method, we can use downsample, we can start their variation. All are good. Yeah, each one give you a different answer to a problem. Here I use standard stoppage criteria. You can play with different spline method. Yeah, there are two. You can use natural spline. You can use even higher order spline. See what you got. Okay. But all of this are already with a method selected. Like I selected the natural spline. I selected all that. And a very interesting method out of this set is the ensemble EMD. The ensemble EMD is an interesting method that almost simulate the real true ensemble of trials. So that will be the subject of the next class. So here we try to establish confidence limit. What we come out of this is that we find that the answer we got with or without intermittency are roughly about we all see the prominent features like annual cycle, monthly cycle, half monthly cycle, and the standard deviation, the confidence limit are reasonably tight for most of the energy containing components. Yeah. And out of this, we also get an indication of optimum range of shifting parameters. Okay. So we get a lot out of this simple exercise. So the next time we're going to discuss this ensemble EMD. Ensemble EMD is a great improvement over EMD that we use now. Does it have problem? Yes, it does still have problem, but nevertheless, it is a step forward. Okay, so we'll stop here, and next time we'll discuss ensemble EMD. Okay, all right. Thank you very much. I will entertain some questions. Anybody has questions for the presentation this class? Any questions?
Yes, sir.
Yeah. Go ahead.
Algorithm, 6 step. You mentioned 6 step. Can you show your algorithm or 6 step? You mentioned 6 step to solve your harmonic, but you do not show it until now. Your algorithm of computing. Can you show it?
Is, anybody? Excuse me. I do not fully understand. You ask about the algorithm?
Yes. How to compute? You have mentioned that 1, 2, 3, 4, 5, 6 steps to compute harmonic.
Harmonic. I never compute any harmonics.
What? HHT.
HHT.
You have mentioned any algorithm do you use?
Oh, any algorithm I use? Yeah. The method that I use, next time I will ask Mr. Su to demonstrate in the class. So at the beginning of the next class, Mr. Su will demonstrate the software we use, okay? The algorithm we use to compute the components. All right? Mr. Su will select a sample data. We will demonstrate how to use that software. Is that your question? How to compute, how to go through this computation?
Yes, but I prefer 1, 2, 3, 4, 5. Step 1, step 2, step 3.
Oh, you want the
Step 4, hey.
You want the user's menu? Okay.
I like it raw.
Sure. We will try. I think if you have that software, there's a README file. Is there a README file? No. Maybe I can try. I'll go find a statement that I wrote about 10 years ago on how to use this 1, 2, 3, 4, 5. I'll try. Okay. Thank you very much. But once you see how Mr. Su demonstrates, you should get a feeling. I always think that the learning everything is like learning swim. Yeah. If you don't jump in the water, you'll never learn it. Okay. I can explain the theory of how to swim. You move your hands, you kick your feet, and all. I have shared with you experience that I had. I took a course in compressed variable when I was in graduate school. I stopped the top. I scored the top in the class. Yeah. Every test I get almost perfect. Yeah. So I was very conceited that I really know compressed variable in and out. But turns out the compressed variable course I took was very theoretical. The whole book has only 2 pictures. One picture is a horizontal and vertical axis and dots. So this is compressed variable. This is real axis, is vertical axis. The second picture I had in the book is an arbitrary shape and a circle. This is a Riemann mapping theory can map the arbitrary circle to arbitrary data into a circle. Every statement, every class, we cover only theoretical things. So by the time I finish that, I can prove every one of the theorem, but I have never done a problem. And as a result, to this day, I don't do problem very well. So I know the theoretical swimming very well. So I advise you for this particular course, please, once you get the tool, please try it on data. And once you try on the data, you'll find more questions, and I can answer your question. You will learn more. And by doing the problem, you also learn more. So that's why I think it's important for you to do that. And once you go through that, and once you do a few problems, you will not follow my 1, 2, 3 steps. You will have your own 1, 2, 3 steps. Okay? Did that answer your question? Okay.
Show me next time.
Okay. See you next time. Goodbye. Okay.
Sorry.
Yes.
Actually, we also have a question about the software.
Sure.
Yeah. So I asked instead of our student. So she downloaded the software named WHHT on the website.
Yes.
but we can't see the README file, and we don't know how to use.
You don't know how to use that. We're going to demonstrate that next time. So make sure you install that software, so that next time you can follow. Okay.
Yeah, thank you. Yeah, thanks.
Yeah. Sujidong, could you give a set of data and also put that set of data on the software? Okay. Okay. We'll put a set of data on there so that the next time everybody have the same data, same software, then you can follow the steps. Okay?
Yeah, thank you.
We'll post a set of data there. Any set of data. Give it to the Mika. Okay. All right. Okay. Yes? Go ahead. Sure, sure.你说 ensemble EMD 啊？我们还没有教到 ensemble EMD. Okay, could you hold your question until I finish the lecture? Okay, you're way ahead of us. Okay. All right. Okay, if there's no question, then the class is dismissed. Thank you very much. Yeah.